Thank you so much, Clyde. May I request everyone to mute, please, so that we don't have that background noise wherever you are. So welcome everybody to this, this number 4 in the series. Clyde has already made the background introductions. I just want to remind you, if you can look at your agenda, that we have 4 speakers. We have Regis from University of Zimbabwe, also working in part with Michigan State University. We have as well Regis, senior agronomist, Cook Fertilizer in Canada. We have Adnan Bargaz, who is a professor at the University of Mohammed VI Polytechnic in Morocco. And then we have Kent Martin, who is working for Martin Agronomic and Environmental Consulting, LLC, in the US. So those are the speakers. You have their topics. I don't have to go through their topics, and I will immediately invite to kick us off, Regis Chikowo, Unlocking the Hidden Potential Through Integrating Fertilizers with Organic Nutrient Resources in Infertile Soils, with a focus on Africa. Over to you, Regis.
Thank you very much. Good morning, good afternoon, wherever you are. It's a privilege to be the first speaker. So my topic today is unlocking the hidden potential through integrating fertilizers with organic nutrient resources in fertile soils. And in many cases, fertile soils are the only soil resource that farmers have. So we have to do something about it if the farmers have to remain as if those are smallholders have to remain in farming. Next slide, please. Yeah, so we know soils are the best resource for agriculture. And also, there's been so much movement in terms of research in genetics. Management has improved in agronomy. But the environment, the biophysical environment becomes a huge thing in Africa, especially in Africa, where the yield gets become so huge. So we know farming systems in Africa are really underperforming. We have germplasm that can, of corn, of maize, more than 10 tons per hectare, but we are still operating around 1 ton per hectare. So that's of big concern. Next slide, please. Next slide. So yeah, so this slide is showing where the problem is. Neighboring farmers, one across the river, one across the road, where maize, one is getting 1 ton per hectare, the other one is getting 4 tons per hectare. So it's not, it has nothing to do with rainfall. It's nothing to do with soil moisture. You know, they could be using the same germplasm, but getting so huge differences in terms of productivity. That applies to legumes as well. Barely half a ton of grain yield, yet we know we can easily, with the germplasm available at the moment, we can go to 1.5 tons and beyond. Next slide, please. Yes, so I really want to talk in pictures because they speak 1,000 words. So that's myself excited in the field. Some experiment we did. We can actually see that with some NP fertilizer, you actually see some nice green maize that gives 5 tons of maize. And then with no NP fertilizer, you barely get 0.5 ton of maize. And I call that an NP fertility yield gap. You do not, in this case, you do not need to apply any liming. It really is just about nice weeding, good timing, and you get a comfortable, a nice, handsome 5 tons per hectare of corn. So when there are no chemical imbalances, no pH is not a problem, aluminum toxicity is not a problem, we get very nice responses to fertilizers. I can say, I'm not sure that it's a bit blocked there, but all I'm trying to say is where you can see it on the slide, it's a fertilizer solution. simple fertilizer solution, you are there. A farming household with 1 ton, with 1 hectare farm is likely to be able to meet its calorie requirements, its food requirements, food security on that small farm simply by applying the fertilizer at the right time, and the solution is there. Next slide, please. So, this slide sums it all. That we can have, in this case, I've put 3 scenarios. A low, very poorly responsive soil, low soil fertility status, a soil that is not yet degraded, medium fertility, and another field where you actually have a nice response to fertilizers. Now, the extreme left, the low soil fertility field, you can actually see that the dark bar there is where the farmer has done everything. And fertilizer has been applied, phosphorus, the potassium, all the micronutrients have been applied. And yet, the farmer is not able to breach the 2 tons per hectare. Now, imagine the fertilizer is expensive, you have invested so much. 2 tons will not make up for the lost yields, lost gains in responses. So it's a fundamental problem of poor soil fertility that we have to deal with, especially when that's all the resource that farmers have. I'll illustrate that with the next slide, please. Yeah, so that's basically a soil factor yield gap that we are seeing there with a similar investment in fertilizers. Farmers side by side, one gets 2.5 tons per hectare. That becomes a soil fertility problem. My internet is playing games, but I hope it doesn't cut off. Next slide, please. Okay, so is there a panacea for poor soils that barely respond to fertilizers? What are our extension messages? What do we say to the millions, to the thousands of smallholder farmers that we're working with? Where when we go to their fields, we see pathetic, very poorly growing maize or any other crop. So we tell them to rehabilitate soils. And we know we need to put in organic resources, organic materials. So we can rehabilitate soils through growing more legumes with high quality, that produce high quality organic materials. So grow more legumes against a background where small farms are small and farmers are desperate to meet their calorie requirements. The other thing that we can do actually is rehabilitate soils through application of manure. Manure in its different forms. It could be animal livestock manure, it could be compost manure. The point is we want to recapitalize soil organic matter, which will make fertilizers respond much more. So what are the opportunities for this kind of recapitalization through biological processes? In many of the farms where we work, farmers do not have enough livestock to produce enough manure to make a difference. So we have to then go and lean towards biological systems, and that really means integration of legumes. Next slide, please. Yes, so this is the old story that we all know, where even if you have virgin soils, you open those soils with annual tillage, within a very short period of time, soil organic matter will bend. Soil organic matter will actually reduce substantially. It's much better when the soils have got clay content that is more than 30%. But in many of the granite-derived soils, where the capacity to store that carbon, the capacity to protect that carbon from microbial attack is weak, then we can be sure that within half a decade, we'll have lost a substantial amount of this initial soil organic carbon. So this becomes the key big issue. We know soils with light textured soils have no capacity to store carbon, but we need to annually cultivate them. Next slide, please. Looks like there's a lag time between changing of slides. Next slide. Yes. So I'm talking from Harare right now, and a lot of the farms are based on granite as the parent material. So the granite-derived soils are really weak. I mean, they do not have high clay content, and therefore you find many farms with soil organic carbon which is very low. For example, one of my students a couple of years ago established that in one of the communities, nearly 50% of the farms had less than 0.4% carbon. And the story becomes very interesting when you do experiments on these different soils on a chrono sequence or within the same environment, and you start looking at nutrient use efficiencies. Let's see that in the next slide, please. Yeah, so on the left, you actually have a farm with a field with 0.35% carbon, and the other one is about 0.9% carbon. You can actually see that if you see this slide, when you have, it's barely without any nutrients, you are not producing anything compared to the other much richer field which can sustain nearly a ton of maize. And then this is the problem, where manure alone is not doing anything because it's not supplying nutrients in critical mass, or the mineralization potential rate is well below the nutrient demand by the cereal crop. And then you do everything, you apply manure, nutrients and everything. Within the short term, you are only getting 2 tons of maize after all this kind of investment. And trying to continue producing crops on such soils without a rehabilitation strategy becomes very difficult. So response fertilizers, the manure is very poor in the short term on acutely deficient soils. This is soil which is still much healthier, and you get these huge responses from less than a ton here. With fertilizer, you get several-fold increase to your investments in terms of manure or in terms of NPK fertilizer. Next slide, please. Next slide. Yes, we also did another experiment where we know with rainfall variability, it's a rainfall water, soil water becomes a critical limitation in crop production to nutrient use efficiencies. So we have conventional tillage, conservation agriculture with furrows, and conservation agriculture with basins. So one of the experiments we carried out along nutrient gradient, basically so many fields in one of the communities. And we actually found that, next slide please. When you do conservation agriculture, when you do manure application, everything else, you get very little on very poor soils. I can see this is a bit bled, but what we are basically seeing is that application of manure becomes critical. And in this case, actually, there is more response to your fertilizers with a bit of in situ water storage through basins, conservation agriculture. So these are some of the interventions that are making a difference on farms that are very infertile. Next slide, please, as I move to the last few set of slides. So with this, we can actually see, if you look at the y-axis, the NPK's yield minus all these other treatments, It's only when you apply manure, NPKSM, it means NPKS plus manure, that's when you begin to have a positive effect. So therefore, manure is a key resource in these infertile soils. But the impediment is you need to be able to apply that manure for quite several times before you start to get consistent response. Next slide, please. Yes. So what are the entry points? We rehabilitate soils through harnessing nitrogen, through biological nitrogen fixation, so integrating legumes in cropping sequences. Repeated application of manure is a key at ameliorating these soils that would not directly respond to NPK fertilizers. So I'll show in the next few slides how we are integrating legumes on the farm. So next slide, please. So legumes, many of participants would probably relate with this. The legumes, we have got nodules where we have got thousands, millions of these nodules where we basically reduce dinitrogen gas to ammonical form that is absorbed by the plant. And you see some nice green plants, which is an indication of a lot of protein. Next slide, please. Which basically shows what I'm talking about. Really, in the nodules, I could sometimes talk to farmers as the many factories. And when we begin to see that the red pigmentation, then we are into serious business in terms of reduction of dinitrogen gas to ammonia form. Next slide, please. And with this integration of these legumes, so this is soybean at scale on a smallholder farm. Basically, you tend to harness, in excess of 60-70 kgs of nitrogen, which becomes a free source of nitrogen. And with good management of those crop residues, we are likely to build high quality soil organic matter in the long term. Next slide, please. Next slide. Yes, and some of the options I just want to show here is, this will be a slide of farmers learning how to grow peanut, groundnut well, which means double row cropping. It means good population, which basically reduces soil loss, better infiltration of water, less soil erosion, and it means we are likely to be able to increase soil organic matter. And in the long term, if we do these cereal legume rotations, we tend to raise soil organic matter even on these light textured soils, and that leads to better responses to inorganic fertilizers. Probably next slide, please. We are getting to the last now. Next slide. Yes, so there are other options where we can integrate the shrub legumes. The shrub legumes like pigeon pea have got much more biomass than the crops like soybean and groundnut. And with this, we can actually accelerate the rehabilitation of the poor soils. The next slide, please. And the next slide is basically showing that one of the key issues is about root biomass. These shrubs actually end up with a lot of root biomass in the soil profile, and this is very key in the long term in the rehabilitation of soils for increased fertilizer use efficiency. Next slide, please. So once we do all these interventions, basically we are trying to eliminate soils that are acutely deficient in fertility, that are acutely deficient in soil organic matter. And with that, we graduate to better soils that are where we can actually be assured of high fertilizer use efficiencies. And with that, next slide, please. So this is my way to conclude it, that it's a difficult working with soils that are very degraded, but looking at different options basically that are available, we are likely to make it. It's a mountain to climb, but we've seen examples in the farming communities where we work with farmers coming from food deficits scenarios to use of these sustainable intensification technologies towards self-sufficiency on very small farms. I thank you.
Thank you so much, Regis. Unfortunately, you've used all your minutes, but we have enough, hopefully, to answer the few questions I see up here. And I would like to immediately invite Shemi to read out the questions that you see, so that we can get responses from Regis. Shemi.
Thank you very much.
Hello, I think
Shemi, you seem to have a connectivity challenge.
That we have posted here is, am I coming through better now?
Now you are coming through, yes.
Yeah,
now you are.
Yeah, we can hear you.
All right, perfect. Regis, the first question is concerning the treatments that we had on one of your slides that indicated you applied NPK and then additionally sulfur and 2 micronutrients. Are you recommending these nutrients without soil testing, and what was the basis for adding those secondary and micronutrients?
Yes. Well, okay. In some of these communities where we do our research, I mean, you literally can go in I mean, you can do soil tests as well and see they're very deficient. Especially zinc is really a problem. But so after 70, 80 years, when these farms have been opened and continuous cultivation each year and harvesting, you can almost be sure that these micronutrients are now deficient, especially when farmers are not using adequate organic resources, then it becomes a problem. So one of our objectives basically was try to get water limited yield potentials in these environments. So we had to basically eliminate these micronutrient problems.
Thank you very much. Then we have 2 interrelated questions. And the first question is seeking clarification on the site where the trials were located, which seem to be very, very low in organic carbon, ranging from 0.35 to about 0.89. If you could probably give a little bit of a background of the nature of those soils and where the location is.
Yeah, thanks very much. I just made a choice to use these granite-derived soils from northern Zimbabwe, where, you know, it's a whole community with soils. You barely find a farm with soil organic carbon greater than 1%, 1%, 10 grams per kg. So, but with thousands, millions of farmers getting their livelihoods out of this kind of soil resource. I could have also chosen to work with these sesqui oxides, highly leached soils with high clay content, but still, and after having cultivation for many years, you still have soil organic carbon not exceeding 1.5%. So these are all difficult soils. Actually, the granitic sands are much easier to work with because they normally do not have aluminium toxicity issues. It's mostly pH problems that are easy to correct with some bit of liming or manure, but not any chemical problems that are too difficult to solve. So this is why in these same communities, a lot of farmers have managed to sustain their livelihoods on such material that you think is good for building, as building a building resource, building material.
So time is a challenge here. Shemi, do you?
I think Regis might want to just quickly respond to one question on the relevance of no-till or conservation agriculture on some of the poor soils that farmers still need to manage every year, especially with managing weeds and also the need to cultivate to break the hard pan in the plow layer.
Yeah. So we then need to contextualize. So when with conservation agriculture, minimum tillage on these very soils, we are trying to protect as much as we can soil the soil organic carbon, which the threshold, I mean the upper ceiling will remain very low. But the benefit we are basically seeing is about time. I mean, farmers then timely apply the fertilizers, the farmers plant in time, and all those accrue the benefit to see benefits in terms of productivity. But again, I can assure you, do not expect anything where you increase organic carbon to double what you find on those soils, because they are very leaky. But what we see basically at the action level is farmers tend to manage those fields much better. They apply the fertilizer in a targeted format. So there's some precision agriculture, and you see neighboring farmers, one getting 1 ton per hectare, the other getting 5 tons per hectare. And a lot of that is ascribed to precision agriculture plus conservation agriculture.
All right, thanks so much, Regis. Ed, I'll cross over back to you.
Thank you so much, Shemi. Thanks so much, Regis. Stand by other questions if we get time. So just stand by. And now
sure.
We are now moving to Regis' presentation. So Regis, welcome to give your presentation, please. The use of microorganisms to improve PU's efficiency.
Thank you very much.
Yeah. Sorry, that's a wrong one. Inhibitors of urease and nitrification, controlled release coatings, microbial inoculants for nitrogen and phosphorus. Over to you, Regis.
Thank you very much. When we are talking about inhibitors and controlled release coatings, we are talking about enhanced efficiency products. So next slide, please. And well, actually, 2 slides down. And next, please. And the definition of an enhanced efficiency product is a product that has characteristics that allow increased plant uptake. And it doesn't matter what, whether it's nitrogen or phosphorus or whatever it is. When we do have increased plant uptake, then that means the potential of nutrient losses to the environments, as well as, leaching runoff, are minimized compared to a reference product. So for nitrogen, for example, when we are talking about a reference product, most of the studies use urea as a reference product. So next slide, please. When we do come to the 4R nutrient stewardship principle, where the right rate is used to get the appropriate yield goal, soil testing and recommendations, nutrient removals and budget, nutrient interactions and balanced fertility, enhanced efficiency fertilizers can play a role. And the same thing with the right rate, the right time, and the right source. And I'll try to cover, there is a very limited time, but I'll cover with a couple of slides those principles for you. Now, why we want enhanced efficiency products is, as you can see, it doesn't matter when we apply the fertilizer, the crop is, and this is from Western Canada, but it applies to any environment. There is no plant uptake until we get, into 2-3 weeks into the growing of the plant. So the whole idea of using enhanced efficiency products is to protect our resources, fertilizers, until such time as the plant starts utilizing them. Next one, please. So there are 3 types of enhanced efficiency products. We have uncoated, slow available fertilizers that contain nitrogen. And those have been around for years and years and years. We have physical coating or barrier around soluble fertilizers, such as sulfur-coated urea, polymer-coated urea, or combination products. And then we have stabilized materials, such as nitrification and urease inhibitors. So next one, please. So when it comes to the inhibitors for urease and nitrification, I'll go through the process very quickly. Next one, please. When it comes to volatilization, the process is a hydrolysis of urea primarily. You can see you need water, and it's mediated by an enzyme, urease, that converts urea into ammonium, but at the same time, it produces that carbonate molecule, and the carbonate molecule tends to increase the pH in the vicinity of the urea granule. As you can see in that graph, when the pH climbs above about 7.6, 7.7, as the pH increases, the ammonium in the soil solution dissipates, and in its place, we have the production of ammonia. And there is an example on the right-hand bottom showing a soil with pH of 7.5, where we applied urea and with the urease hydrolysis, the pH climbed to 9.5. And there are all kinds of examples for that. Where we have 2-3 units of pH increase when hydrolysis takes place. We all know that ammonia is a gas, and that's where the issue is. So next slide, please. The way to protect fertilizers, urea from urease. If you go into the literature, you can see there are a number of mechanisms or strategies: use of urease inhibitors, slow release forms, irrigation shortly after application. Actually, that's a really excellent example. If you can irrigate with 0.8 of an inch, which is what, roughly about 2 centimeters of water right after application, the losses, the volatilization losses very much, disappear. However, the most common practice has been the incorporation of the fertilizer into the soil. Why? Next slide, please. When we incorporate urea into the soil, especially at 3 to 4 inches depth, we still have the same reactions. We still have the formation of ammonia. However, there is all that soil mass on top of where we have applied the fertilizer, and that absorbs the ammonia that is being generated. Next slide, please. When it comes to nitrification, leaching, and denitrification, of course, this is the process of nitrification, where ammonium is converted through Nitrosomonas and Nitrobacter to nitrite and nitrate. This is also mediated by an enzyme, ammonium monoxygenase. And of course, nitrate is subject, depending on the environments, it's subject to either denitrification when we have saturated soils, or to leaching, so depending where we are, and actually the soils that Regis described, if there is moisture, if there is excess of moisture, those sandy soils, they will be subject to quite a bit of leaching. Next slide, please. So the nitrification inhibitors, what they do, as you can see, is they block the microbes. They actually stop the action of the ammonium monoxygenase, and as a result, we don't have the conversion of it slows down the conversion of ammonia to nitrate, and consequently, we are protecting our fertilizer. I just want to share with you some examples from my research in Western Canada. I started doing research with nitrification inhibitors 7 years ago. And the next slide demonstrates to you the principle of an enhanced efficiency product. In this slide, we broadcasted urea, and we broadcasted urea treated with Nbpt. And we had two rates. What was the recommended rate that was provided to us by a soil testing laboratory? And then the 70% of the recommended rate. And this slide compares urea applied at 100%, the recommended rate, that's the white bars, compared to Agritane treated urea or Nbpt treated urea at 70% the recommended rate, and we have statistically the same yield. And that's exactly when I give presentations to farmers, I tell them, hey, look, there's got to be a reason for you to use an enhanced efficiency product. High volatilization environment. If you're using a nitrification inhibitor, there's got to be a lot of water. If you don't have these conditions, you don't need that. But pardon me. Nevertheless, this demonstrates how when you apply, an enhanced efficiency product, and it does what it's supposed to be doing, you can. That's how you save. You have a more efficient fertilizer, and save some money if you wish. The next slide shows you the average yield increase of urea treated with Nbpt or Agritane compared to untreated urea. You can see that spring broadcasting, and we got an average of 11.9, say 12% yield increase. Of course, like you can see on the left-hand side, there are some sites where you don't get the increase. Why? Because there was no environment that would, require that would lead to volatilization losses. But there are environments where there are high volatilization losses, and as a result, you can see you get a really high yield differences by using an enhanced efficiency product. The next slide now, that is something that I wanted to show you. Super is a fertilizer that contains a nitrification inhibitor in addition to volatilization inhibitor. And that is, again, it shows you how if you are in situations where you have denitrification losses or leaching losses, how a nitrification inhibitor can prevent those losses. Again, on average, there was 13% yield increase compared to untreated fertilizer. So now the next one, I would like to move into the controlled release coatings. And that next one, please, will be the polymer coated urea. And polymer coated urea fertilizers, the nitrogen release is controlled by diffusion. And the major factors that will affect the release, of course, will be the coating thickness, temperature, as well as moisture. So depending again, for example, in the turf and ornamental industry, the coatings are much thicker than they would be in the agricultural industry because, we're irrigating the lawns and the turf and soil ornamentals much more frequently than crops. Next slide, please. Now, where are the polymer coated fertilizers? Where should be applied? In a high volatilization environment. And those environments are all over the world. And it's kind of interesting, maybe this is a terminology that it's not used, seed row safeners, but what happens in Western Canada, 65 to 85% of nitrogen or some of the nitrogen is applied during seeding. And if you are applying nitrogen with the seed and you want to apply 80, 90, 100 kilograms per hectare, if you use a polymer coated urea, that gives you an excellent protection. And that's what a safener, the term means it safens the use of urea when it is placed with the seed. The key points for polymer coated urea, the cool conditions at seeding will slow the release of nitrogen from polymer coated urea. You have to have contact with soil moisture and consequently, just broadcasting polymer coated ureas sometimes is not the best strategy, and that's why it's recommended that there is a blend of polymer coated urea with uncoated products, because if you need to fill up, it's a pouch, and you need to fill up that pouch with water in simple terms in order for the diffusion to take place. So it has to be into contact with soil, and it has to be into contact with moisture in order to generate release. So keep that in mind. And I want to share with you the results from some a large number of experiments on the next slide that the Alberta government has carried out in the province of Alberta in Western Canada, using not only using the products, but also Len Krzyzanowski, who is the scientist who did this, and he was kind enough to share this slide with me from one of his presentations. He mentioned that what is really important is the economic benefit that you get in addition to the yield benefit. And as you can see on the right-hand side of the slide, as I mentioned, seed row safener is really, where there is a tremendous fit in our environment. Why? Because our environment tends to be a little bit drier. If you go into the Midwest of the United States, then of course, with corn broadcasting and banding the fertilizer, broadcasting and incorporating, I meant to say, will give you the maximum economic yield. So the next thing that I would like to cover very briefly, and I must admit I'm not an expert in biofertilizers, so next slide please. I would like to, oh, I'm sorry, that was, yeah. The next one, what are biofertilizers? Biofertilizers are substances that contain live microorganisms. When those are applied to soil surfaces, seeds, roots, and soil, they colonize the rhizosphere, or they get inside the plant and help to improve soil fertility, while at the same time, they stimulate plant growth by increasing the availability of plant nutrients and, of course, growth substances to the host crops. Bio is from the Greek words bios, which means life. So biofertilizers, that's exactly what it means. What are, next slide, please. What are biofertilizers? Are comprised of bacteria, blue-green algae, and fungi, or fungi, however you want to pronounce it, which are either together or separate. And they can be made in solid, powder, granular, carrier material, liquids. Now, one thing you have to make sure you clear up in your mind is biofertilizers should not be misunderstood for organic fertilizers such as compost that Regis was talking about in his presentation prior to mine. It's not a compost, animal manure, or manure extracts. Biofertilizers are microorganisms. Right now, I have the opportunity, I'm working here with a biofertilizer that solubilizes phosphorus. And in my career, I've been involved in quite a bit of research with that type of microorganisms. Next one, please. the types of biofertilizers, there are two major classifications: nitrogen fixing biofertilizers and solubilizing and mobilizing biofertilizers, such as for phosphorus and potassium. We are all very much aware of the symbiotic relationship for rhizobium. You know, like, I mean, you're going to grow a legume, you need to have, in most of the cases, of course, or all the cases, a rhizobium which in symbiosis with the legume root will contribute to the uptake of nitrogen by the crop. There is non-symbiotic free-living nitrogen fixers such as Azotobacter, Peyeringia, Clostridium, and Azospirillum and Enterobacter species. There are other bacteria that can fix nitrogen. So you've got to, you know, there are a whole bunch, you know, like cyanobacteria that are made up of Anabina or nostoc, which in association with Azolla can be used for rice cultivation. Azolla is a heterosporous water fern, and in association with Anabina, can fix in the range of 140 to 100 kilograms per hectare when used for wet rice cultivation. Then we have the solubilizing and mobilizing biofertilizer, micronutrient biofertilizers, and plant growth promoting rhizobacteria. That's exactly what I'm working on right now. And the next slide, please. And I got, that's the last slide. Why biofertilizers? They increase the yield and nutrient availability through the contribution of symbiotic nitrogen fixation or non-symbiotic. What you have to remember, though, I've seen research with Azotobacter that it was fixing nitrogen really nicely in the absence of nitrogen in the soil media. The moment that you added some nitrogen, they stopped working. So keep that in mind. But there are a lot of, you know, non-symbiotic, and there is an example in West Africa, and it's called Nodumax, that it's economically profitable at $5 roughly per application compared to 20 times what you would apply with fertilizer. Anyway, plant growth promoting rhizobacteria or PGPRs are considered biofertilizers because of their biofertilization potential. And similarly, bacteria like Bacillus, Penibacillus, the PGPR I'm working on with right now, experimental, has 4 Bacillus species as PGPR, plant growth promoting rhizobacteria. The PGPRs produce phytohormones, and as a result, they can cause an increase in plant foliage, root elongation, fruit yield, and plant microbe symbiosis. And also there are other microorganisms that can have a potential for prevention of plant pests and diseases, bioremediation, and water stress resistance. So with that, thank you very much for the opportunity to give the presentation, and I hope I left some time for questions.
Thanks so much, Regis. Actually, you've done wonderfully on time side. We have 2 minutes plus the question time, so we are good. Thanks for walking us through enhancing efficiencies through improving plant uptake, reducing nutrient losses, and your coverage of biofertilizers, which was in more detail than you think you are going to do. Thank you so much. I would like now to hand over to Shemi to capture some of the questions that are coming up.
Thank you very much, Regis, for the very insightful presentation. I want to start by picking on 2 related questions on the unintended benefits, effects, of some of the enhanced efficiency fertilizers. The first one is there a long-term negative effect of continuous application of polymer-coated fertilizers on the soil? And have you also reviewed the effects of nitrification inhibitors on the microbial activity and also the diversity of the microbial biomass in the soil?
Okay, so let's start with continuous application of polymer. Now, in order to register polymers, they have to be biodegradable, so in the long term. So I don't see any negative effect of a continuous application from that point. So, pardon me, as long as polymers are, registered as fertilizers and are, that means that you shouldn't be concerned about it. Okay. And I know I spent 3 years of my career back in the 80s working on a venture team that was developing a polymer coated urea for, at that time, ESO fertilizers or Exxon. So, and that had to be a biodegradable, and I believe ESN, the environmentally smart nitrogen the nutrient is producing, is also biodegradable. So I see no issues with that. Now, the next one was about, I'm sorry, I didn't catch that second one, I apologize.
It's in relation to the effects of inhibitors on the microbial biomass and diversity.
Okay. Is there is that about the surface pH?
No, it's I think it's on the chat box rather than the question and answer chat box. Let me read again.
Yes, please. Thank you.
Did you look at the effects of nitrification inhibitors on microbial activity and diversity in the soils? No, not as yet. Well, I shouldn't say no. We do have some work that we carried out with Agriculture Canada. It was done in the laboratory, and we found out that it does. The application does not change the biodiversity of micronutrients. Thank you very much.
Microorganisms. My apology.
Right. I want to have an additional question in relation to the soil surface pH at which ammonia volatilization is no longer a major concern for broadcasting or surface banding of urea.
Well, we have examples from soils that have pH of 5.5 where there is, it's not that surface pH is much. I would say, when you go down to acid pHs, definitely the volatilization slows down, but it never stops. And we do have examples, from where pHs of 5 and 5.5. Actually, Montana State University has done an excellent job of doing so, and they have a soil, for example, with pH 5, where they leave urea on the surface, apply water, and the pH increases by 2 units, and as a result, there is some volatilization. But the thing is, as I mentioned to you, what is the key is the moisture. If the surface is bone dry, you're not going to see very much volatilization losses. Where we do have a lot of losses, and people don't realize that, when the surface is kind of dry, but that there is a morning dew coming up. And the research, again, from Washington State University show that if you have 1/10, say, 2 millimeters of moisture, your losses, volatilization losses, can be up to 70-75%. Whereas with 20-25 millimeters of rain or irrigation, your volatilization losses can drop to 5. So I think it's the moisture that is the key. But if you're looking for a pH, I would say 4.5 would be something where, you know, a pH for you to consider.
All right, thank you very much. For the interest of time, we'll take just one question, which addresses a component that you have not specifically touched on in your presentation, the option of S-coating on industrially produced neem-coated urea, you know, for enhancing nitrogen use efficiency. I think this is of particular interest in India, where neem coating of urea is widespread and a well-adapted technology.
Well, I have a little bit of experience with sulfur coating, you know, and yes, especially, and my experience has been from the work that I've done with turf and ornamental, you know, where you prefer the sulfur coated urea rather than the polymer coated urea, especially on golf courses, because people walk and can destroy the polymer coated urea. There is, you know, now, can you go for that, for enhancing? It will enhance from the point of view that it will reduce the losses of nitrogen through the coating and, of course, through the acidification. But to be very honest with you, I cannot say with confidence, yeah, go for it. Sorry about that.
All right, thank you very much, Regis.
Welcome.
Ed, let me hand over time back to
Thank you. Thank you.
Thank you so much, Regis, for a very, very lively set of issues and responses.
Thank you.
Yes, at the end, Shemi will be summarizing some of the key points coming out of the four presentations. It's now my pleasure to introduce Adnan. So we are now moving to much more specific things, much more specific presentations. So Adnan's presentation is focusing on improving P use efficiency. Over to you, Adnan.
Okay, so thank you so much, Edward. I'm really very delighted and grateful to the Canada Africa for our initiative, for having me in today's online series webinar. So my name is Adnan Bargas, Assistant Professor at Mohammed VI Polytechnic University. So during my presentation, I will provide an overview about the importance of the need for optimization of the rhizosphere microbial interactions responsible for improving phosphorus use efficiency. So next slide, please. So we all know about the agriculture production relies and will continue to rely on fertilizers and irrigation to meet the need for the ever increasing population and overall food security. N and P are really the most important needed as macronutrients, and specifically for P, which is the topic of this presentation, which is a renewable resource that whose use efficiency will expand and will exponentially trend up, okay, in the few coming decades. The next slide. Because P is a macronutrient that is essentially needed for crop, so a shortfall of it drastically result in significant loss of crop production. So thus it's important role in food security. So the next slide, please. So at the physiological level, P, so along with potassium and nitrogen, so being the most important macronutrients, so has functional key roles in plant as a structural element for DNA and phospholipids, but importantly as the building block for ATP and ADP as the source of energy for all living cells. Yeah, the next slide. So two examples may be highlighted so as to concretely showcase the important role of P. So in two main phenomenon, which is carbon fixation, that catalyzes the photosynthesis phenomena that's securing life on Earth with carbohydrate and oxygen produced. So the second is the biologically nitrogen fixation, or the biological nitrogen fixation, either symbiotically or in its free way with the free microorganisms or associated microorganisms. So through the nitrogenous enzyme, so complex that requires P. So for the conversion of atmospheric nitrogen to ammonia needed for plant growth, for protein formation. So the next slide. So highlight in this also the importance of P as source of energy for the biological nitrogen fixation, which is considered to be a considerable amount of inputs in both agriculture and natural systems. So whose rate was found to be influenced by P status in the soil, and not only station, but importantly the availability of P in the soils. And this is much more important in grain legumes, so in terms of crop production. So where P or where nitrogen fixation is really rely on the availability of P in soils. And we can see in the graph at the right side, so the important nitrogen fixation rate in many legumes, and that the shortfall of P may decrease so this rate. So please, next slide, please. Okay, so however, so P is important because P is the very the very limited nutrients and immobile nutrients in soil. So P is known for being low available, for being immobile, even though soil might be rich in P. The available fractions is always challenging for root absorption. So this low phosphorus availability is exacerbated in acidic and alkaline soils, and P is often retained in soil particles and divalent cations, like in acidic soil, aluminum or iron, and alkaline soil so bound with the calcium. And this map so clearly shows the potential potential in most world's agriculture soil, with the red spot are being the most P deficient soil in the world. So the next slide, please. So this is the case of many countries and many countries so worldwide, in South America and Africa. So where P deficiency and aluminum toxicity so goes together, they often occur together, affecting significantly both arable soils and crop production. And this example was given specifically to land dedicated to common bean production, or bean area affected by these two inseparable constraints. The next slide. So to cope with this situation of low phosphorus deficiency or availability, so plant nutrition needs to be optimized, or I mean systematically optimized, taking into account not only P as a fertilizer, but also the crop, soil, biochemistry feature of the soil, and the many management practices. And this, of course, this webinar is hosted for our stewardship nutrient. In this conceptual model, so P can be optimized through soil-based management, so which actually fits with the 4R solution. While the second gap, which is in green green highlighted, calls for maximizing roots and rhizosphere interface efficiency for improving phosphorus use efficiency through the exploitation of the below ground potentialities, which encompass mainly roots and associative microorganisms that are specialized in P mobilization, solubilization, or mineralization, or in general microbes that mediate P in the soil. The next slide, please. So the rhizosphere optimization will rely on the soil exploration. I mean, in terms of surface, and this soil exploration ability is driven by the roots and both soil and root associated microbes. So that will help increase soil exploration, mobilization of immobile nutrients, or immobile P. We can also talk about P solubilization of strongly mineral P, mineralization of organic P, but also the immobilization of P that is immobilized in microbial cells. The next slide, please. So soil microorganisms contribute significantly to enhance phosphorus use efficiency. This is known evidence. By solubilizing, mobilizing, or mineralizing in general, mineralizing the inaccessible P, especially that P stands as the most immobile nutrient that is closely depleted at the vicinity of roots. So in order to be uptaken, it must be really at the vicinity of the roots, which make the P absorption by roots a challenge for both roots and P mediating microbes. And the next slide. So generally, there is a need for plants and microbe to cooperate together as to cope with low phosphorus availability, especially by deploying either specific or general strategies. So where roots tend to expand and harbor the most important and specialized microbe species that mediate P at the true level of the rhizosphere, notably the endorhizosphere. So we talk about endophytic, ectorhizosphere, or most importantly at the rhizosphere, at the rhizoplane interface. So where P is mostly depleted. So the next step, the next slide. So among the strategies that allows higher phosphorus use efficiency, one can talk about the production of microbial organic acids, okay, that are well known for their high ability to make P more available. So encompassing a variety of chemically different organic acids, notably the gluconic acids, known for its higher ability to solubilize P as compared to other acids. So with fungi being the most important microbial forms that can synthesize gluconic acids, so as compared to the low extent in bacteria. So the next slide, please. Phosphatase activity or acid phosphatase activity was also demonstrated to be involved in higher P acquisition and uptake. So it's in an experiment on wheat inoculated with PSP and rock P supplies. So we found that root acid phosphatases were induced in response to inoculation with P solubilizing bacteria, and this really happened at the 40th day after sowing, and we can clearly see the significant difference between the inoculated and non-inoculated wheat, and this was directly proportional or indirectly proportional to Rhizosphere available P that decreased over time, which means that there is a significant use of solubilized P that was indicated in shoot P as an indicator of higher solubilization and uptake by plants. And we can see clearly the halo of the P solubilizing bacteria we have used in this study. Next slide, please. So in this slide, I'm specifically showing the variation in terms of root morphological traits that were also significantly influenced in response to inoculation with a P solubilizing bacteria as compared to mineral P alone. So we can clearly see that inoculation has really increased the root traits, which I mean the root length, root surface area, diameter. And we can see this clearly in the picture at the right side, so where the root length has almost doubled due to inoculation and the rock P fertilization as compared to non-inoculated plants. So thank you. Next slide. Likewise, so here I provide similar variation in terms of root length. So here we can see clearly the positive effect of PSB, so that really generated higher root lengths after 42 days of growth. Next slide, please. So PSB have also positive effects on the photosynthetic activity, as attested by the positive correlation between chlorophyll content and shoot P content, either total P or inorganic P in leaf tissues. So this positive correlation between those two parameters indicates probably a positive and indirect influence that tight below and above ground in inoculated as compared to non-inoculated plants and rock P fertilization, which is a good indicator for positive physiological effects. Next slide. So not only availability of P from rock P can be improved. So this figure shows the positive effect of P solubilizing bacteria on increasing the uptake and the uptake of P from triple superphosphate as a mineral P, and we can clearly see that co-application of P solubilizing bacteria together with TSP produced or yielded better as compared to non-inoculated soils, and this is is clearly seen in terms of shoot P that significantly increased as a response of this dual application of TSP and PSB, so as compared to the control. Thank you. Next slide, please. Increasing P uptake by using potent microbial cells or strands is an evidence for no. At the same time, so using P efficient crops and or P facilitating cropping system has also been an applied research priority, especially at the interface of the rhizosphere, so where crop diversity so can contribute to a beneficial to a beneficial rhizosphere heterogeneity, leading to activating the below ground processes. By saying below ground processes, we also say either roots or biological components of the soil that are responsible for P acquisition. So in the next slide, an illustration of the crop crop association or mixture, okay, where one crop, the crop at the left, where one crop at the left has the ability to make P more available through acidification of the rhizosphere, and this by acid phosphatases, for example, including phytase, which is a specific enzyme activity, through organic acids, as we have seen in microbes, which all facilitate P to the neighboring plants, which neighboring plants, basically the neighboring P inefficient crop, which means also that this facilitation may also be enhanced by niche complementarity that may occur during this association. Next slide, please. So in this slide, and in the context of crop diversification, an experiment on soybean, intercrop in soybean and wheat and low phosphorus availability, okay, shows that shows an increase in phosphorus acquisition, which was actually clearly seen at the level of should P content. But the most importantly is that in both intercropped crops, either soybean or wheat, so we have noticed an increased microbial diversity, either fungal diversity or bacterial diversity, but most importantly, the bacterial diversity that really increased in both intercropped crop. Next slide, please. And so one of the most important results in the study is that the either fungal community or bacterial community significantly correlated with a few root traits and also physiological traits. And we can see that, for example, fungal community correlates significantly with soil P and should P, and that bacterial community also correlates with root dry weight, which means that there is really a positive correlation that led to a higher P acquisition due to increased or stimulated microbial diversity in such intercropped system. So the next, please. So similarly, intercropping, another study on intercropping and maize and common bean and low P soil exhibited higher performance. So under low P availability, which is confirmed by the land equivalent ratio, okay, indicating an advantage from intercropping over 2 seasons. So which indicates the importance of mixing crops that are compatible and that they can use efficiently the they can use efficiently so nutrient resource in soils, so either over time, so without really creating any competition, so in terms of either of yield or nutrient acquisition. So the next slide, please. In this slide, I would like to emphasize that crops, so with higher ability to induce internal mechanisms, so internal mechanisms, sorry for this, internal mechanisms, so that stimulate the internal use of P, as well as its distribution in plant tissues, which means that, for example, in this study, so we highlighted the important role of acid phosphatases, either diversity or activity of acid phosphatases in nitrogen fixation, and we found that using crops, so with high P efficiency, will perhaps induce internal mechanisms such as the phosphoanal pyruvate phosphatase that we successfully localized in nodule, in Phaseolus vulgaris nodules, which correlated with many parameters, notably nodule respiration. And we know that nodule respiration is very can determine nitrogen fixation. So so this is still puzzling, and research on those internal mechanisms that lead to higher P acquisition and wiser distribution across organ is necessary. So the next slide. So very briefly, this slide shows many genes or transcript genes of phosphatase activity, either plant and microbial, like the beta-propyl phosphatase, that we successfully localized in nodule tissues. So with the preliminary evidence of their importance in nitrogen fixation and phosphorus availability inside the root tissues. So the next slide. So as a summary, sorry for this figure, so there are the axis title and the title that are not really very clear here. But as a summary of my presentation, so it is quite evident that achieving acceptable crop production will crop production, so while increasing nutrient use efficiency, not only phosphorus use efficiency, because the root rhizosphere efficiency approach might be applied on almost all the nutrients. So this imply also increasing nutrient use efficiency and lowering the environmental risks. So might be, so with available evidence already exists, maybe achieved by maximizing the root interactions or the root rhizosphere interaction, while taking into account the fertilizers, the management practices, the crop, either P or efficient or PN efficient crop and cropping systems, and also the soil biology, including the microbial component of the soils. So as a conclusion, in the next slide, so farming by beneficial microbes is now a challenge for a sustainable agriculture, so which relies on selecting, the right mixture, so on selecting the right strands, on selecting the right mixture or consortium, on also targeting the right crop, the right place, whether seeds or leaves or roots, but importantly, the right type of carrier that might be a fertilizer. In our case, it might be a P fertilizers that is compatible to roots. So all these features or principles align with the 4R solution, and I think that there seems to be a need to find out integrated plant nutrient management systems for designing, testing, and hopefully proposing innovative integrated plant management systems for the near future. And with this, I would like to thank you so much for this opportunity.
Thank you, Adnan. Thank you. High speed, yeah. But you managed, you managed to get to the end. Thank you so much. So Shemi, we do have just over 7 minutes for this part. So if you can take that into account as you put together the questions. Over to you, Shemi.
Thank you very much, Ed. I'd like to start by a question related to the effects of different crop cultivars in responsiveness to inoculation with P solubilizing bacteria.
So, sorry, Shami.
Adnan, the question is asking clarification on the how different cultivars vary in their response to inoculation with P-solubilizing bacteria.
Oh yes, yeah. So this aligns with one of the conclusion points, is that the right crop does also matter for proposing a beneficial, and productive strand. So no, the idea is experimentally. So when targeting a strand, for example, in wheat or in cereal plants, we have the assumption that the strand will work good for wheat, for maize, but conversion or effort on one crop in a given experiment or a given research project, this may open opportunity to test them on other crops, either in the same family or in for example in legumes as well. So when talking about PSB, for example, in wheat, and after many efforts, we got to select one consortium, for example. We can also test this, for example, in legumes, as to verify if, for example, this PSB might increase phosphorus availability. That will also get benefits for nitrogen fixation, knowing that P is very important for nitrogen fixation. So there's also opportunity to test in many crops, but the results repeatability is not really the same.
All right, thank you very much. And second question that we have is seeking clarification on the effects of phosphates making P available from organic matter, then also the issue in relation to organic acids making P available from soil, mineral forms of P. Which of this is a better strategy for African agricultural soils?
Yes, so this is quite wide. So yes, it's not really easy to give an answer, a clear answer on this, but the mechanisms developed by strands, by beneficial strands, knowing that roots also have the ability to produce acid phosphatases and secrete also organic acids. But in terms of linking this to African soils, so we can say also that these mechanisms are site specific. So if the soil is organic, rich, and there are plenty of organic P in it, so maybe the rhizosphere in the rhizosphere interface, so mechanisms that are related to phosphate mineralization will prevail as compared to P solubilization. But in African soil, I'm not really going to generalize this, because they are diverse, and we cannot really proportionally or directly link mineralization or solubilization to a specific soil. But I can say also that in acidic soil, maybe organic acids and solubilization mechanisms will prevail as compared to mineralization processes.
All right, thank you. And we have a more general question also on suitability of various P sources for IPH calcareous soils. So if we consider the major sources such as TSP, DAP, SSP, which ones would be more suitable for calcareous soils?
Yes. So experimentally speaking, and given the available finding, so there are evidence that there are not really yet strong evidence of a possible and generalized use of combined mineral fertilizers or pea fertilizers with microbes. So there are kind of research, basic and fundamental research in this aspect, but they are sometimes aligned, but they are also in another hand they might be also controversial. But in terms of suitability of a certain mineral as compared to other, I really don't have a clear answer in this. But based on my own experiment, I use TSP as a pea-based fertilizer, and they found really promising results in this. But we are not yet in the stage of using it as a career, but compatibility between both resources are needed, so to be studied in this way. So anyway, so we are ambitious, so to find so what career might be suitable, or what careers might be suitable for this combined application.
All right, thank you so much.
Okay.
I think that covers the questions that we can handle with the limited time that is available.
Thank you so much.
Thanks so much, Shemi. So Adnan, thank you so much. You opened it nicely by telling us why P is important, being involved in all the critical functions of a plant. And then you contrasted it by saying, however, it has low availability and it is one of the most limiting nutrients. And then you walked us through how to optimize it, from soil management through crop genotypes, through microbial strategies, through agronomic practices, including strategic intercropping. Thank you so much.
Thanks. Thank you.
I have learned something myself, and I really appreciate that.
Thank you. You're welcome.
Right. I would like now to hand over to Kent, who is now moving us from P to S. We are going now to Kent, over to you.
Okay, well, thank you everyone for the opportunity to present to you guys today. Want to make sure I'm coming through loud and clear, Ed. Can you hear me fine?
Yes, you're good. You're good.
So what I've noticed in the last few years, I've been working specifically on sulfur with shell thiogrow technologies for the last roughly 10 years. Prior to that, worked with Kansas State University in soil fertility and research. And what I've noticed during that time is that sulfur has become much more a part of research programs, much more awareness about sulfur. And so we see a lot of activity and interest being generated there. If you'll move to the first slide. We think about the sulfur background in general, and of course we know it's essential. We consider it the fourth most important nutrient next to nitrogen, phosphorus, potassium. As we've heard the last few presentations, the first two mentioned sulfur as a part of the limiting nutrients and some of the components of other fertility issues. And so we know the importance of it. Part of structural plant parts, enzymes, amino acids, chlorophyll synthesis that we see from the yellowing on the plants as we look at sulfur deficiency. Crop growth, we see that importance from shortened internodes and other issues that we see when the plants are deficient. And of course, we notice that it's a part of yield. It's directly tied to yield. Of course, so as we grow greater yielding crops, we see more deficiency occur. And then the generation of proteins and oils. I think this becomes important, as we heard in the first presentation, about growing higher yielding crops, pushing that yield gap, and growing oil crops, growing different crops that are important for African agriculture that will utilize the sulfur and not only make it important for application, but also reduce that reserve of sulfur in the soil. If you'll go to the next slide, please. I don't think I've ever seen a sulfur presentation without the cycle. And of course, the sulfur cycle is a very difficult one to comprehend. As we look at it, it looks somewhat like a nitrogen cycle. But of course, as we see, we have the input portions in dark blue. Of course, atmospheric deposition has always been important, but then also, as we've heard earlier today, animal manures, other organic components, plant residues, all become important for this organic sulfur that ultimately leads to the sulfate for plant uptake and utilization. I'll focus on the input side from a source standpoint. We'll talk about some fertilizers, both the sulfate sources and elemental sources, but also want to draw your attention to the red portions of loss, where we can have significant loss in different portions of this cycle, and really want to try to minimize the loss potential as much as we can, especially in some of the coarser soils that we would find in Africa. If you'll move to the next slide, please. This one I'll just touch for a minute, but this goes back to the atmospheric deposition. And as we've cleaned up the air, cleaner air initiatives, we see the sulfur deposition decreasing over time. And this is an example from the US that we've seen where Clean Air Act has decreased the amount of sulfur that we're getting out of the atmosphere and greatly cleaned up our atmosphere, but also has significantly reduced that deposition of sulfur. And so what we see is deficiency in closing in around that area of industrialization, where more and more soils across the country are becoming deficient. Next slide, please. As we look at probably the second most widely considered issue is the removal from crops. And we notice that because sulfur is strongly related to yield, we notice as we grow more and more yield out of each unit area of land, we're pulling more and more sulfur from those soils. And so that has been another one that as we draw that down and as we push that yield gap, we see a greater benefit from added sulfur to push that. Also, more and more legumes being grown in rotations. The sulfur is a very, very important component in the legume, the yield generation and the protein generation in legumes. So that becomes additionally important as well. If you'll move to the next slide, please. So as we think about fertilizers, so all that was kind of the background. As we think about the fertilizer and the sources, really we have two major types, I'll call them. We have the organic sources and then the inorganic sources. And by the organic sources there, I'm talking about food waste, animal waste, residues, municipal waste, all of those kind of components that are significant contributors to sulfur. What we notice is that in many cases, those products are being processed in some way or composted in some way, and many times have some addition of sulfur to them to improve them and then utilize them as a sulfur source. I'll go into a little bit more detail on that later. Then, of course, the inorganic sources being sulfate and elemental sources, probably the most commonly used and widely used source there is ammonium sulfate, of course, gypsum, ammonium thiosulfate, superphosphate, and others take up a portion of that as well. Then on the elemental side, we have sulfur bentonite. That's probably been the most widely used elemental source in the past. It has the longest history, I would say. Then of course, raw elemental sulfur and others. As we look into technologies that have been recently developed for sulfur application, we think about co-granulation. We think about things like microessentials, and the products I've been working on with Shell ThioGrow recently is co-granulated products with nitrogen. So a urea and elemental sulfur product and high sulfur containing elemental product. These are micronized, so we have very small particles, and I'll go into how that interacts in just a minute. Next slide, please. When you think about the organic portion, of course, that's 95% of the sulfur in the soil. And as we heard from the first presentation, we think about how that organic component influences the availability of all of our nutrients and sources to the plant. That's critically important. When we hear that the organic component is decreasing in African soils or too low to supply sufficient nutrients to the plant, we think about how this is influencing the sulfur. So when we look at low organic matter, low soil test sulfur, coarse soils, those are all indications that sulfur is going to be an issue from the organic component. Then we think about where does this come from? Where is this existing at? Well, the animal residues, and we heard that maybe we don't have enough animals to supply sufficient manures for that. So maybe we think about microbial biomass, we think about plant residue. Can we increase that carbon in the soil to build the organic matter to supply more nutrients to those plants? We know that sulfur is highly correlated with carbon and nitrogen, and therefore the organic measurement in your soil test and the understanding of that organic measurement is important as we think about how that supplies the sulfur to the plants. Next slide, please. Going on to the inorganic side, sulfate was the first one that I talked about. And of course, this is how sulfur is absorbed by the plant roots. This is a relatively small portion, but we find this in the soil solution. We find it in some cases absorbed to the mineral surfaces. Sometimes we find it precipitated. So it can be in several different forms in the soil, but this is how we see the plants take up the sulfate. It is mobile in the soil, so of course losses, as we think back to that sulfur cycle, the losses are very important there to consider. What kind of soil do we have? Do we have a coarse soil? Is it well drained? Do we think that when we apply a sulfate source that it will stay, or that it will move with a heavy rainfall event and possibly be moved offsite either laterally with erosion or moved down through the soil through leaching? Next slide, please. Then as we think about the elemental sources, I want to cover the bentonite first because it's the longest standing one that we've used in the past. This is sulfur that has a matrix of bentonite clay. And of course, as we know, bentonite clay is a high shrink swell clay. This has a range of sulfur particles within that clay, and as the clay brings in moisture, it swells until it ruptures the pastille, and then of course at that time it's releasing the sulfur from that pastille. This takes a relatively large amount of moisture to make that happen, and it's a fairly slow process. On the other hand, the co-granulated, which is kind of on the newer end of technology for sulfur, is sulfur dispersed in a matrix of another fertilizer product like like phosphorus or nitrogen. Then that co-granulated product can dissolve away and you're left with sulfur as a fertilizer source. Next slide, please. Real quickly, oxidation. And so I'll kind of move into the elemental side because that's where there's the least understanding of these sources. On the elemental side, oxidation is required, and there are a range of microorganisms responsible for this. We don't even know all of them. What we do recognize as probably one of the more common ones or most thought of is thiobacillus, but of course, these microorganisms generally are present in your soils. And if you'll move to the next slide, we see an illustration or an image of these microorganisms on the right-hand side. And these microorganisms that are native to your soils, what we see is as we apply elemental sulfur, we see a spike in the microbes that are doing the oxidation for us. And so in some ways you get a priming effect from the application of elemental products to build that microbial species in the soil to make oxidation faster in the future. Of course, as we think about the product itself, small particle sizes are important for this, for access of the microbes to the sulfur particles within the pastille. You'll move to the next slide, please. This one is very simply a surface of a pastille and looking at low and high thiobacillus on how they have interacted with that surface of the pastille surface of the particle within the pastille to oxidize that sulfur. Next slide, please. When we think about the small particle sizes, as we saw in the blue illustration earlier, that small particle size greatly increases the oxidation rate. And as we look at the data on the right here, we see that as the size gets smaller, we can have an incredible amount of oxidation early in the season after application. So in some cases, this study saw 80% of sulfur oxidized in 2 weeks and 82% in 4 weeks with a 60 micron size. So in many cases with these newer products, the goal is to try to tailor the particle size to fit the oxidation rate that's desired. Next slide, please. As we look at the difference in the bentonite as one elemental source and the co-granulated as another, this is my illustration on the right of the bentonite swelling to release the sulfur particles. And then on the left, we see that with sulfur particles interspersed with a mix of a co-granulated product, then that co-granulated product dissolves away and you have the elemental products on the surface. If you go to the next slide, please. This one is simply to illustrate that particle size or pastille size is highly important on the degradability of the product and the ultimate release of that product. And so what we see is the larger the pastille size, the slower it degrades and longer it takes to become available. Of course, one important thing about this is you think about product selection and availability and how you use these products. It is, does this granular, this particle size match the blended products that you intend to use, and will it stay in a nice, even, homogeneous mixture rather than settling out? And that's a very big important point as you think about the pastille size. Next slide. As you look at the particle size within the pastille, that becomes very, very important for the oxidation, as we've discussed before. And what we see in some of these cases with bentonite, particle size in most products range from 60, and this says 800 microns, but for the most part, they range about 60 to 150, maybe 200 microns. And then in the products that I've been studying the last 10 years or so, we're averaging about 20 to 40 microns in size, so very much smaller. Next slide, please. If we want to look at an illustration of this, this is a Cyclops microscope image of sulfur bentonite and the product that I've been studying called Super S, which is a 75% sulfur. This is one that has urea as the matrix in it. And you can look at these particle sizes and you can see how small these particle sizes are in the Super S. You can see the size of the sulfur bentonite particles. This becomes important as you decide on which product to apply and what your overall strategy of application is going to be. If you want a long-term slower release, or if you want a faster release, something not as fast as ammonium sulfate, but faster than sulfur bentonite, those all become a part of the question. Next slide, please. This is simply a cross-section of a granule of the Special S, the product that I just showed. And you see in there the white specks are the sulfur and the dark is the urea that will dissolve away and be the product on the soil surface. Next slide, please. This one is probably my favorite slide in the presentation because this is where the sources get a comparison against each other. And what we see on the left-hand side, we see a line that goes straight up and over. This is ammonium sulfate. This is an illustration of a sulfur product that is immediately available. Now, if we could look at that slide over time, if we had a heavy rainfall event, because that's in sulfate or in the sulfate form, that may very well decrease after that rainfall event. So there is, anytime any of these products get to a sulfate form, that line can move down with loss. Then on the other end of the spectrum, on the green line on the lower side, we see sulfur bentonite. this is one that is slower available, but will be released over a long period of time. So in some cases with a multi-year cropping system, some case where you don't want to have a lot of application, you just want a long, steady release, sulfur bentonite may be your product of choice. The work that we've been doing recently is to look at trying to stay ahead of the crop uptake curves. The red and black lines are IPNI data for corn and soybean uptake. So we've tried to develop products, and this goes along with micro essentials as well, that stay ahead of the crop uptake curve, but not too far ahead, so that there's not too much loss. So it can protect you on both sides of the loss potential. Next slide. This one is just to illustrate, as we heard in the last presentation, some benefits of different things in terms of rooting depth, phosphorus availability. We definitely see some added value with sulfur additions in these soils. Next slide. And then, of course, as we think about soil testing, and I think we heard another question earlier on about soil testing and the challenge of soil testing. It is an issue with sulfur because the correlation and calibration data is relatively poor with the soil test. It does give you some good information, but an actual sulfur soil test should be coupled with understanding of organic matter in the soil, as well as some idea of what the plants are telling you. So if you go to the next field, or sorry, next slide, and you look at the field in this image, you can see the areas of sulfur deficiency. That's usually expressed as a chlorotic condition on the upper parts of the plant leaves, slow growth, shortened internodes, typically on hillsides, leached areas, eroded areas, anywhere where organic matter is low. And most typically, as we look at these areas, we try to find the condition exhibited in the field and make sure we understand that area, couple those plant tissue samples with soil samples and other things to understand where we find those sulfur deficiencies occurring, many times year after year in much the same area. And then we can understand where we need to focus our sulfur fertilization on those fields. So if you go to the next slide, this is the end of the presentation, but just wanted to point out that in the African soils, as I understand them, there's a great need for sulfur, and the sulfur awareness is greatly increasing as we go through time. We've had studies in Africa looking at sulfur fertilization, and of course we've seen a wide range of responses and definitely a wide range of soil conditions in Africa, but an area that we expect to see an increasing awareness and an increasing desire for application of a range of sulfur products. So this presentation was a subset of about a 6-hour presentation that I've previously given. So if there's any questions or thoughts, or anyone want to have a conversation on this, please feel free to contact me. I'd love to have a one-on-one conversation about it. Thank you very much.
Thank you. Thank you so much, Ken. This has been very systematic walk through on the various sources, organic through sulfate, the elemental, with a lot of detail on the elemental side, which has been really, really helpful. I think the reminder that yield increases, which we all aspire for, also means that sulfur is drained out of our soils at probably this proportionate levels as we get the yield increases is really, really important. I would like to hand over to Shemi to handle to summarize some of the questions that he has picked up. Yeah. Over to you, Shemi.
All right, thank you, Ed. Thanks, Ken, for the very insightful presentation. The first question is on clarification. You do mention 2 terms in your talk. One is special S, and the second term is super S. What is the difference?
Yes, that was a mistake on my part, actually. Those are one and the same. One was a previous name of another. So apologize for that, but that is the same. It is an 11% nitrogen, 75% sulfur product. Urea is the co-granulated product for sulfur.
Right, and one remark is more of a comment, which is recognizing that there is a lot of effort in research and fertilizer promotion on the macronutrient side and the micronutrient side, but when it comes to the middle, secondary nutrients, there seems to be less emphasis there. Do you agree? And then the second question is, we concentrated on the first R of the four, which is the right source, and there's a question about the general concepts and principles of the method of application, which is the right place, and also the right time in relation to S.
Yes, those are all very good. I appreciate the comments about micronutrients like zinc, boron, those kind of fertilizer additions. And of course, we do see those being added to some of these products as well, and very important, especially my understanding in Africa, is zinc has a high level of importance there. And so that is definitely one that we see, and I think we saw in the first presentation, that has been added as a part of a complete package. So definitely important there. The second one, as far as the 4 R's, so I focused on the source, thus being a nutrient source-based series that we have today. But of course, these products all have a different interpretation and understanding of what we would do in terms of rate, timing, and method of application. Of course, we know that some the sulfate products have a challenge when you put them with the seed. And I think I can't remember, I think it was a second presentation that we talked about seed placement a little bit. The elemental products you can. There's been much effort to develop products that can be seed placed, and so that is definitely a consideration that we need to take as we look at that, not damaging the seed in terms of salt generation, but also being able to supply some of these secondary and micronutrients to the seed. Then on timing, we think about, if we need a rescue application of sulfur, then obviously a sulfate product is your product of choice because it's immediately available. If you need something that you could apply in a one-pass scenario as you're running your planter through the field, then a co-granulated elemental product is probably your product of choice. Then if you think about a pass of fertilizer application months before, then maybe sulfur bentonite is your product of choice. And so that gives you a perspective of how these different sources might influence the timing of application that you would apply. Most generally, we think of rate being fairly constant throughout these, but then as we think about long-term products like sulfur bentonite, in many cases, people will increase the rate because the length of time of oxidation and availability of those products may span over 2 or possibly 3 growing seasons. So then the rate also becomes highly dependent on how we choose our fertilizer source.
All right, thank you so much, Ed. I think we have come to the end of our time allocation, and I will hand over to you.
Thank you. Thank you so much. I would like to take this opportunity to thank our presenters, our resource people, and Shemi, of course, for translating it and helping handle the questions. I hope everybody has benefited from this session. And at this point, I would like to hand over to Clyde and maybe Labonia as well, but to Clyde. Clyde, please, can you take over?
Slide. Hello, excellent session this morning. We also, I think, had one of our technically perfect sessions, or as close to it as we could get. So I think we're getting more and more comfortable with the technology. So I appreciate the staff here and the efforts that have been made to make sure this went off without hitch. And also, thanks very much to the speakers. You know, from my perspective, part of the 4R Solution project is to make sure that farmers, extension workers, scientists in Africa have access to all of the technological concepts and ideas that are cutting edge around the world. And I think the presentation today did an excellent job of outlining what's available globally, and that African smallholder farmers should have access to these products when it makes sense for them on their farms and in their crops and geographies. So I just wanted to mention that the next webinar, number 5, on-farm research and extension methods, will be held on Monday, October 19th, in the same time slot of 8 a.m. to 10 a.m. Eastern time. And please keep an eye on the 4R Solutions social media and our website for registration and the agenda as we finalize the details. I wanted to remind everybody that all of this webinar material will be available on the 4rsolution.org website, and that's a recording of the session, all of the presentations, and I urge you to look at some of those presentations. There may be more detail available in some of the presentations than we were able to fit in today. And also, we will take all of the questions that were posed today on the chat and through the Q&A function of Zoom, and we will ask the panelists to provide more detailed written answers. So look for those on the website. If your question wasn't answered today, it should be answered on our website. And of course, the speaker bios are also available there at 4rsolution.org/4R-webinars. Another reminder that our 4R Champion program is up and running. These are grants of $500 or $1,000 to anyone in sub-Saharan Africa who's interested in doing a 4R micro project. And again, the information on that is available on our 4R website, 4R Solution website. So please stay connected with us through the website, where you can also hook into our newsletter and other material. So Ed, I also want to thank you and Shamie for the great work you did to moderate the session and to handle our questions and answers. And I just, for closing, just turn it over back to Lavanya. Okay.
Okay, Ed, thank you for conducting the session, and thank you to all the attendees. So we'll see you in October. We can close the session now.
Thank you.
Thank you, and bye-bye, everybody. Thank you.
Thank you. Bye.
Bye.
Okay, thank